Hello guys, this is Dr. G here, and today we are going to continue our discussion on chapter 7, which is basically on chemical reactions. And today we are going to specifically talk about oxidation reduction reactions. So this is basically uh, a category of chemical reactions that is based on oxidation and reduction of different chemical substances. If you recall from the things that we discussed in chapter 7, we already learned about chemical reactions and how to balance these reactions. And also we try to categorize the chemical reactions into 5 classes of chemical reactions. Mainly these 5 classes are combination reactions, decomposition reactions, single replacement reactions. Fourth kind is double replacement reaction, and the final kind is combustion reaction. So we didn't talk about any oxidation reduction reactions in those 5 categories of chemical reactions, but basically these oxidation reduction reactions are a broader classification of chemical reactions, and in fact uh, about 90% of the chemical reactions that we see in nature can be identified as oxidation reduction reactions. And also, from the 5 classes of chemical reactions that I discussed before, uh, 4 classes of chemical reactions falls under oxidation and reduction reactions. The only uh, chemical reaction category that does not fall under oxidation reduction reactions are double displacement reactions. So combination reactions, decomposition reactions, single displacement reactions, and combustion reactions are actually, or they can be classified as oxidation reduction reactions. So as you can see, these oxidation reduction reactions are everywhere in nature. They are everywhere in nature, and we are going to talk about uh, these reactions in more detail in this chapter. And so in this slide I have a simple example for oxidation reduction reaction. So this is basically the rust formation when oxygen is in the air reacting with iron metal. So basically in this reaction you can see an oxidation and a reduction happening. So therefore we categorize these rust formations as oxidation reduction reactions. And the chemical reaction that happens in this rust formation is given in this slide. So as you can see in here, iron is reacting with oxygen to form iron oxide. So in this reaction, you actually can see both oxidation and reduction happens at the same time, and therefore we call these reactions oxidation reduction reactions. So basically these oxidation reduction reactions are extremely important in nature. Most of these oxidation reduction reactions are associated with energy reactions. So basically generation of energy as well as use of energy uh, is or can be categorized as oxidation reduction reactions. So uh, most of the reactions that we see in nature could fall under oxidation reduction reactions. So it is very important to understand how to identify these reactions and how to balance these reactions. So let's talk about these reactions in more detail in this slide. So as I mentioned before, uh, in oxidation reduction reactions you have 2 things happening at the same time: oxidation and reduction. Both oxidation and reduction happens at the same time. And then uh, this oxidation and reduction is basically opposite to each other. Oxidation and reduction is opposite to each other, and you can define oxidation and reduction by using electrons. Okay, or you can say you can define oxidation and reduction by uh, by using electrons and uh, figuring out what happens to the electrons during the reaction. So basically, as I mentioned earlier, oxidation and reduction is basically directly opposite to each other. And oxidation is known as loss of electrons, and reduction is known as gain of electrons. So oxidation is loss of electrons and reduction is gain of electrons. So it is very important to know these two things. Oxidation is loss of electrons and reduction is gain of electrons. So some people remember these two concepts using the two words oil rig. So oxidation is loss, reduction is gain of electrons. So that is basically what oxidation and reduction means. So in an oxidation reduction reaction, you always have a chemical species losing electrons to another chemical species, and therefore we have an oxidation reduction reaction. Therefore we have a oxidation reduction reaction. Let me take another example and explain this to you in more detail. So let's say you have a chemical species called A. Okay, so this A is losing an electron. So if you are losing an electron, you should become A plus. You guys know that. So basically this reaction right here, A going from A to A plus, this is oxidation. And here is that electron that it lost. So now let's talk about reduction. So let's say you have something called B in this same reaction, and B is basically gaining this electron. It is basically gaining this electron. So let's remove that electron and give it to B. So if B gains an electron, it becomes B minus. So A is losing an electron, so we call it oxidation. B is gaining an electron, so we call it reduction. So this reaction right here is your reduction. This is reduction. All right, so in this oxidation reduction reaction, as you can see, A is losing an electron, so that is oxidation. B is gaining that electron, so that is reduction. So that is how you define terms in this reaction. So in oxidation reduction reactions, you basically have both oxidation and reduction happens at the same time. You have both oxidation and reduction happens at the same time, and also they are opposite to each other. Oxidation is loss of electrons, reduction is gain of electrons. And then some more chemical terms or technical terms that you might want to remember. The species that is going through oxidation, so A is going through oxidation, as you can see. So we call it the reducing agent. So the species that is going through oxidation, we call it the reducing agent. Why? Because A is the agent that helps the reduction, right? A is the agent that helps the reduction. So that is why we call it the reducing agent. And B is the agent that helps the oxidation, right? So we call B the oxidizing agent. So these are some of the other technical terms that I want you to remember. So in this reaction, A is going through oxidation, and we call A as the oxidizing agent because A is helping B to reduce. So we call A the reducing agent. And B is going through reduction, and B is known as the oxidizing agent. Why? Because B is helping A to oxidize. And in this reaction, A is oxidized. And B is reduced. B is reduced. B is reduced. So you might want to remember these technical terms, because when we talk about oxidizing reactions and oxidation reduction reactions, we will use these technical terms. So it is important that you remember these terms. All right. So let's go back to our discussion. So in this reaction right here, A is losing electrons to B, so A is oxidized. B is gaining electrons from A, so B is reduced. Okay, so we have an idea about oxidation reduction reactions. So basically, two reactants, or it could be two or more actually, two or more reactants are exchanging electrons, so that whenever there is an exchange in electrons during a chemical reaction, we call them oxidation reduction reactions. We call them oxidation reduction reactions. So now we know that now we basically know how to define oxidation and reduction. So oxidation always loses electrons, reduction always gain electrons. But here's the tricky thing. I mean, by now we learned how to balance reactions, we learned how to write chemical reactions, but we never used electrons, right? We never used electrons. So basically, we don't see electrons in a chemical reaction as electrons. So it is very difficult to use just the gain or loss of electrons to identify oxidation or reduction. So therefore, we might want to have other ways to identify oxidation and reduction in an oxidation reduction reaction. So one such way to identify the species that is going through oxidation, or the oxidation itself, is the atom oxygen. Excuse me. Is the atom oxygen. So basically, during oxidation, you basically add oxygens. Okay, if you are adding oxygens to a reactant, that is oxidation. So reduction being the opposite, it should lose oxygens. So if you don't want to worry about the electrons, you can easily figure out what happens to oxygen. So if a half reaction, or if a part of our reaction adds oxygen, we can say that that part of our reaction is oxidation. And if a part of our reaction is gaining oxygens, that is oxidation. And then if the other half is losing oxygens, we can call it reduction. Easy enough, right? But here's the problem. I mean, most of our reactions may not have oxygen, so it could be tricky to only depend on oxygen to categorize oxidation and reduction. So if we couldn't find oxygens in our reaction, what we could do is we could use a different atom. We can actually use hydrogen and figure out oxidation and reduction. So basically, in oxidation, it loses hydrogen, and in reduction, it gains hydrogen. Remember, oxygen and hydrogen, they behave oppositely in oxidation and reduction. So basically, in oxidation, you add oxygens or you lose hydrogens. In reduction, you either lose oxygens or you gain hydrogens. Actually, these two bullet points, second and third bullet point, these two bullet points are very important if you discuss organic reactions. Why? Because in organic reactions, you always see oxygen and hydrogen. In organic reactions, you always see oxygen and hydrogen. So it is very convenient to use these two bullet points. But here's the thing. In inorganic chemistry, we may not see oxygen and hydrogen in our chemical reaction. So in that case, we should have something that is solid to identify oxidation and reduction. Or in other words, when we can't see things like oxygen, hydrogen in our reactions, or how they behave. If it is tricky to understand how oxygen and hydrogen behaves, we should have another hard and fast rule, let's say, to identify or distinguish between oxidation and reduction. So that thing that we could always depend on when identifying oxidation and reduction is this concept called oxidation number. So basically, by using oxidation number, you can easily figure out the oxidation and reduction. So during oxidation, there is always an increase in oxidation. During reduction, there is always a decrease in oxidation number. So that is the best way to identify oxidation and reduction. These two are the best ways to identify oxidation and reduction. And now, I mean, you have heard me talking about these reactions, oxidation, reduction reactions, for more than 10 minutes, I think. And then you might wonder, why do we need to go through all these troubles and figuring out what is oxidation and what is reduction, and what is the significance about it? Here's the significance about figuring out oxidation and reduction. If we could identify oxidation and reduction, it is easy to design chemical reactions. So if you, in the future, you might become chemical scientist, and then you might come up with your own chemical reactions. So basically, when you are designing new chemical reactions, you might want to understand these oxidations and reductions. And also, if you want to I understand the chemistry behind a reaction, it is always important to know oxidation and reduction. That is also significance. And for most people, the most important thing about this oxidation and reduction is that they can be useful in balancing complicated chemical reactions. Of course, if the chemical reaction is easy, don't worry about oxidation numbers or figuring out oxidation and reduction. You can easily balance it using the simple techniques that we learned before. But I mean, if you have a very difficult chemical reaction and if you want to balance it, then you might want to use these techniques, oxidation and reduction, and also things like oxidation number, to figure out what's going on. All right, so next comes the hard part. So basically, the next two slides, slide number 6 and 7, are going to be the meat of this reaction, in this discussion. So if you understand slide number 6 and 7, you will have an easy time in the exam, because in the exam I will always ask for these oxidation numbers. There will be questions about it. And then and also you will use these oxidation numbers to do things like balancing chemical reactions, and also identifying the chemistry of a chemical reaction. So there are so many things that we could do if you know these oxidation numbers. So and also oxidation number is increased. During reduction, the oxidation number is decreased. During oxidation number is increased. During reduction, the oxidation number is decreased. So it is always convenient to know the oxidation number of every atom, and then we can easily figure out the oxidation and reduction. So that is the point of this discussion. So here's the thing. To figure out the oxidation number, you will have to apply one or few of the 10 rules that are associated with oxidation numbers. You might have to use one of the 10 rules that are associated with oxidation numbers. Each of these rules are important in figuring out oxidation numbers of different chemical species. So from here onwards, I'm going to teach you how to figure out oxidation numbers of different chemical species. All right, so let's start. So let's talk about the first rule. According to the first rule, let's read it with me. The oxidation number of an atom is 0. Okay, so the oxidation number of an atom is going to be 0 if the atom is in a neutral chemical substance, and then also it contains atoms of only one element. Okay, so that is convenient. So let's take some examples. Let's go to a different note. Okay, so according to rule number one, if you have neutral atoms such as, let's say, sodium, magnesium, or let's say aluminium, oxygen, or things like, phosphorus, S8, all these chemical compounds are neutral, and the first three, they are basically in the element form, and you only have one type of atom in them. So if that is the case, their oxidation number is always 0. And when you are writing oxidation numbers, we always use a square bracket. So you write the number in between a square bracket. And also, if you have chemical molecules, okay, where you only have one type of atom getting together to form that chemical molecule, then the oxidation number of those atoms involved is also 0. Are we clear? All right, so that is what rule number one is. All right, so according to rule number one, oxidation number of an atom is 0 if it is neutral, okay, and if it is in an atomic state. And also the oxidation number could be 0 in a molecule like O2, O3, P4, S8. The key thing about these molecules is that not only they are neutral, these molecules also have only one type of element, one type of atom. So therefore their oxidation number will always be 0. So here is a simple chemical reaction. Fe reacting with oxygen to form iron 3 oxide. It's a nice, very straightforward chemical reaction. Okay, so in this one, iron is a neutral atom, and therefore the oxidation number of iron is 0. And for oxygen gas, it's a neutral molecule, and also this molecule only has one type of atom. So therefore the oxidation number of oxygen is going to be 0. In other words, both oxygen atoms in O2 molecule is going to be 0. But rule number one doesn't say anything about the oxidation number of this particular iron or this particular oxygen. Why? Because even though this chemical compound is neutral, there are more than one type of atom getting together to form this molecule or this compound. So therefore we couldn't figure out the oxidation number of iron or oxygen in iron oxide at this point. So rule number one is very helpful in figuring out oxidation numbers for these two. All right, I hope that it is clear to you. And then let's talk about the second rule. I recommend that you guys keep a small note somewhere for these 10 rules, so that it will be easy for you to summarize everything at the end. And then in the second rule, it talks about the oxidation number of simple ions. The key term is simple ions. It talks about the oxidation number of simple ions. And what are simple ions, if you may ask? Okay, simple ions are basically a single atom forming an ion. Such as sodium ion or maybe chloride ion. Okay, so those are simple ions. Why? Because these ions only have one atom forming an ion. okay, forming an ion. So those are simple ions. And then the thing about these simple ions is that their oxidation number is equal to the charge. Their oxidation number is equal to the charge. So for sodium ion, the oxidation number is +1 because you have a +1 charge there. For chloride ion, the charge is -1, so the oxidation number is -1. So if you have a let's say ion like oxide, if you have an ion like oxide, O2 minus, you know the oxide ion, right? So the oxidation number will be -2, and don't forget to use a square bracket. And if you have an aluminium ion, the oxidation number of aluminium ion will be what? It will be +3. It will be +3. So basically for simple ions, oxidation number is very straightforward. And then the charge will be equal to the oxidation number. So we went through rule number 1 and rule number 2. They are very easy rules. And then let's talk about rule number 3. Okay, so rule number 3 and 4. These two rules talks about an important atom, which is hydrogen. So rule number 3 and 4 talks about hydrogen. By the way, I forgot to mention that. I mean, when you consider these rules are prioritized. Okay, so rule number 1 has the highest priority, and rule number 10 has the least priority. So basically, in rule number 3 and 4, we talk about hydrogen, and then oxidation number of hydrogen is figured out in both rule number 3 and 4. Here's the thing about hydrogen. Hydrogen can sometimes bind to non-metals. Hydrogen can sometimes combine with metals to form chemical compounds. And if hydrogen is attached to a non-metal, the oxidation number is always going to be +1 for hydrogen. If hydrogen is attached to a non-metal, the oxidation number of hydrogen is going to be +1. So for CH4, you have 4 hydrogens, and each hydrogen is going to have a +1 oxidation number. And ammonia, once again, hydrogen is next to a non-metal, and therefore hydrogen is going to have a +1 oxidation number. So similarly, in HCl, once again, hydrogen is attached to a non-metal. This is a non-metal, and therefore the oxidation number of hydrogen is a +1. The oxidation number of hydrogen is a +1. Are we clear? All right. So the next rule is once again for hydrogen, but when hydrogen is bound to a metal, then the oxidation number of hydrogen is going to be -1. So this hydrogen right here, it is going to have an oxidation number of -1. This hydrogen right here, I mean, you have 2 hydrogens. Each hydrogen is going to be -1. All right, I hope that this is clear. Okay, so doesn't matter what the compound is. You can have hundreds of chemical compounds with hydrogen. If hydrogen is bound to a non-metal, the oxidation number is going to be +1. If the hydrogen is bound to a metal, the oxidation number is going to be -1. So here's the thing. Now you might understand something about this oxidation number. Okay, it kind of looks like charge, don't you think? Okay, actually you are correct. If you feel like it could be the charge, why? Because I mean, it could be complete charges or partial charges, but once again, this oxidation number is closely associated with the electron density and what happens in in a bond. I mean, what happens to electron density in a chemical bond? You know, non-metals are greedy. Non-metals, they are very greedy. So therefore, they usually have higher electronegativities than hydrogen. So if hydrogen is bound to a non-metal, non-metal is going to have the higher electronegativity, which means it is going to steal electrons from hydrogen. It is going to steal electrons from hydrogen. It is going to steal electrons from hydrogen. So let's say you have a non-metal bonded to a hydrogen. So basically, you know, non-metal is going to steal electrons, so therefore it will be partially negative, hydrogen will be partially positive. And what did we learn today? So if hydrogen is bound to a non-metal, the oxidation number will be what? The oxidation number will be plus 1. Did you see that? All right. All right. So same thing. If hydrogen is bound to a metal, you know, metals have a very low electronegativity, so therefore metal is going to have partial positive charge, hydrogen is going to have partial negative charge in this chemical bond, and therefore hydrogen has an oxidation number of -1. It's going to have an oxidation number of -1, which basically correlates to the partial charge on hydrogen. All right, I hope you got that. Let's go to the next 6 rules. So these rules are not that bad, guys, and I'm going to allow you to keep these 10 rules in the exam. Okay, so you might want to study them, but here's the thing, it doesn't matter you write them on a piece of paper and look at them all the time when you're figuring out oxidation numbers. If you don't understand these rules by heart, you're going to have a hard time in the exam. Okay, keep that in mind. So rule number 5 and 6, these two rules are actually some of my favorites. Mainly because they are very easy and we already discussed about them in a different manner. Okay, so let's talk about them. Okay, so rule number 5 talks about the oxidation number of group 1a metals, and then rule number 6 talks about the oxidation number of group 2a metals. So let's talk about them. So according to rule number 5, okay, if you have a let me go to a note and it will be easier for me to discuss from a note. So if you have a group 1a metal, okay, by now you should know what are group 1a metals. It could be lithium, sodium, potassium, rubidium, cesium. Here are the group 1a metals, and they are group 1a, so you know how many valence electrons they have. How many valence electrons do they have? They only have one valence electron, which means in order to achieve the noble gas configuration, they simply have to remove one electron. So all these group 1a metals, they are always looking for a way to lose an electron. So therefore their go-to ion is always +1, not +2, not +3, but +1. So basically we know that in a chemical compound, group 1a elements always have a +1 charge. So therefore, according to rule number 5, their oxidation number will always be what? +1, which is basically their preferred charge. Okay, this is a very important rule. Okay, so and it is an easy rule to remember. Okay, we know that group 1a metals always look for a way to make a +1 charge in a chemical compound, and therefore the oxidation number must be what? +1. So that is a very simple rule. And then rule number 6, this is rule number 5, and then rule number 6 is very similar. In rule number 6, okay, we talk about group 2a metals. And then the group 2a metals are what? Beryllium, magnesium, calcium, strontium, okay, and barium. These are your group 2a metals, and the valence electrons for group 2a metals are going to be 2. So they have 2 valence electrons. So you know now, in order to achieve the noble gas configurations, they always remove 2 electrons, or they will basically donate 2 electrons to someone else. And if you donate 2 electrons, you make a 2 plus sign. You make a 2 plus sign. You make a 2 plus sign. So therefore, in a chemical compound, these group 2a metals are always 2 plus signs. So therefore, in a chemical compound, their oxidation number should be what? Plus 2. Plus 2. So rule number 5 and 6 are pretty straightforward. We already know the charge of group 1a or group 2a metals if they are in a chemical compound. And if we know the charge, we should know the oxidation number, which is basically the same. All right, so now comes the harder part, I would say. Okay, now comes the harder part of this lesson, which is basically the last 4 rules. And the thing about last 4 rules is that they have, especially rule number 7 and 8, they have a somewhat ambiguity. Okay, some other rules from rule number 1 through 6 could change the oxidation numbers of the atoms that we are going to talk about next. So therefore, rule number 6 and especially 6 and 7 could be a little bit tricky. So you might want to pay attention, okay? So let's talk about rule number 7. It talks about oxygen, our favorite atom in inorganic chemistry. Oxygen, because it is everywhere. Oxygen is everywhere. And in rule number 7, we talked about the oxidation number of oxygen. And according to this theory, the oxidation number of oxygen is usually what? It is usually minus 2. It is usually minus 2. There are exceptions though, okay, but the usual situation is that the oxidation number of oxygen is minus 2. So if you take most of the chemical compounds that contains oxygen, things like water, things like, let's say, sodium hydroxide, potassium phosphate, or calcium carbonate, or let's say chromate, potassium permanganate. All these chemical compounds have oxygen in them, and then the oxidation number of each of these oxygens is going to be what? Each of these oxygens is going to be minus 2. Is going to be minus 2, and of course use a square bracket when writing the oxidation numbers. By the way, depending on the number of oxygens you have, in here you have 3 oxygens, so each of these oxygens is minus 2. So overall, these 3 oxygens could have a minus 6 oxidation number. Okay, but I prefer to write the average oxidation number. I prefer to write the average oxidation number for each atom. So you can say that each of these oxygens have a minus 2 oxidation number. But there are exceptions. Okay, and here are some of the exceptions. Guys. We already learned about O2 and O3 from rule number 1. These simple molecules, they only have one type of atom and they are neutral molecules. So therefore, their oxidation number is what? 0. Each oxygen has an oxidation number of a big fat 0. All right. So here are some of the other examples. Things like OF2. Here's the thing. we learned about oxide ion. Oxide ion is O2 minus, right? So therefore usually general oxides have a -2 oxidation number. And if you talk about the electronegativity of oxygen, it has the second highest electronegativity, which means only fluorine is capable of stealing electrons from oxygen. So therefore, fluorine is the only atom that has a higher electronegativity than oxygen. So therefore, when oxygen and fluorine is bound to each other, you know that fluorine is winning. So it will be partially negative, oxygen will be partially positive. So OF2 oxygen has a plus oxidation number. In fact, this is +2. The oxidation number of OF2 oxygen is +2. Okay, that is something important that you might want to remember. That is an exception, and the good thing is that that is the only exception. Okay, why? Because fluorine is the only atom in the whole periodic table that has a higher electronegativity value than oxygen. So therefore, this is the only time oxygen will have a plus oxidation number, because every other atom has a lower electronegativity than oxygen. So therefore, the oxidation number of oxygen will be low. All right, will be negative. In fact, it will usually be -2. It will usually be -2. And then now there are other exceptions such as superoxides and peroxides. So here is a prime example for a peroxide, hydrogen peroxide. For peroxides, the oxidation number of each oxygen is -1. Okay, so for peroxides, the oxidation number of oxygen is a -1. Is -1. Okay, so this is a peroxide. This is a peroxide. And then, of course, hydrogen should be +1 because it is attached to a oxygen. So each hydrogen will be a +1, each oxygen will be a -1. And the other kind we are going to talk about is called superoxides. These are not very common, but you can easily see superoxides with group 1A metals. As an example, KO2. Here is a superoxide. We know that this is not an oxide, because if it is an oxide, it should be like this, K2O, right? Why, if you ask? You should not ask why, because if I ask you to write the oxide of potassium, you should write like this. Why? Potassium, excuse me, potassium is +1, oxide is -2, and then in ionic compounds we learned that when you're writing the formula for an ionic compound, you write the metal first, you swap the charges, you take 2 from oxygen, you put it as a subscript next to potassium, and then you write oxygen, and then oxygen gets 1. So this is the oxide, and this is not an oxide. This is not in fact, this is not your regular oxide, right? So what is this oxide, huh? So this is called superoxide. And then the oxidation number of each oxygen that you have in a superoxide is -1/2. Oh, yeah, it could be decimal numbers or fractional. Okay, so this is -1/2. So potassium can also have a peroxide. Okay, the peroxide is actually KO2. Yeah, the oxidation number is -1. The oxidation number is -1. Are we good? Okay, by the way, I made a small mistake, so let me fix it. -1/2. There you go. Okay, so superoxides and peroxides have a oxidation number that is different. then -2. So I mean, hey, 99% of the oxygens are regular oxide, so therefore, the oxidation number of oxygen will be -2. The oxidation number of oxygen will be -2. And then let's talk about rule number 8. Let's talk about rule number 8. And in rule number 8, we talk about the oxidation number of halogens. Remember those guys? All right. So what is the thing about halogens? So we know halogens actually are in group 7A. They are in group 7A. Halogens are in group 7A. And the halogens that you have in group 7A are fluorine, chlorine, bromine, iodine, and astatine. But let's talk about the more important four. These are the four most important halogens, and then they have 7 valence electrons in their valence band. So therefore, they only need 1 electron to achieve the noble gas configuration. So they are very greedy, and they always try to steal just 1 electron. Okay, so it is their sole purpose to find 1 electron and pair the unpaired electron and make a -1 charge, right? So halogens always make a -1 charge. Okay, halogens always make a -1 charge. So usually the oxidation number is, of course, -1. The oxidation number is -1, but there are exceptions, of course. Okay, especially these things called oxyanions. Oxyanions are things like chlorate, bromate, things like these. So these are oxyanions, if you remember. So I mean, you can replace chlorine with any one of these four other than fluorine. Of course, you can replace chlorine with bromine or iodine if you want. And then these ions usually have oxidation numbers. For chlorine, that is not -1. So that those are some exceptions. And then also, of course, things like Cl2. Okay, so from rule number 1, the oxidation number of these chlorines are 0. Both chlorines in here will be 0. So other than these exceptions, these common exceptions, usually halogens exist in nature as halides, and if you have a halide, the oxidation number must be -1. The oxidation number must be -1. All right, so we learned a lot about the first 8 rules, and then let's use these 8 rules. So in the next step, we are going to learn how to use these rules. And so therefore, in a way, rule number 9 and 10 are the most important ones, because without having rule number 9 and 10, you could be a little bit helpless. Okay, why? Because rule number 9 and 10 basically talks about most of the other atoms. Why? Because in the first 8 rules, we talked about neutral atoms, we talked about simple ions, we talked about hydrogen, oxygen, halogens, and group 1A and group 2A metals, but we didn't talk about any other chemical compounds or ions. So how about them? How about carbon? How about nitrogen? How about manganese? What is the oxidation number of those elements, right? So the oxidation number of those elements usually depends on the chemical compound. So if you want to figure out their oxidation number, you should know this rule number 9 and 10. They are very similar to each other. Okay, the only difference is that rule number 9 is for neutral compounds. Rule number 9 is for neutral compounds. And then rule number 10 is for charged compounds, and usually charged polyatomic ions. Okay, so that is the only difference. So rule number 9 talks about neutral compounds, and then rule number 10 talks about polyatomic ions. So let's talk about it. So according to rule number 9, the sum of oxidation numbers, okay, the sum of oxidation numbers in a neutral compound is 0. Okay, so So the sum of oxidation numbers in a neutral compound is 0. Here is an example. So you already know about water. Okay, let me take a whole new notepad. Let's discuss about this in more detail, shall we? All right. So basically, if you have a neutral compound like water, oxidation number, the sum of oxidation numbers for water should be what? 0. Let's see if it is correct. We learned that usually oxygen is -2, and then hydrogen is attached to a non-metal, so the oxidation number should be what? +1. Okay, and you have 2 hydrogens and 1 oxygen in this chemical compound, and then hydrogen is +1, and you have 2 of them, and then oxygen is -2. When you add these up, as you can see, +2 -2 becomes 0. Okay, so that's how it happens, guys. Okay, that's how it happens. So basically, in a neutral compound, the most important thing is that compound should be neutral. Okay, in a neutral compound, the sum of oxidation numbers is equal to 0. So let's do this for few other compounds. I mean, here's the thing. Water is easy because we already know the oxidation number of oxygen and hydrogen, but sometimes in chemical compounds we may only know 1 or 2 atoms and their oxidation numbers. We have to figure out the oxidation number of the remaining one. Then this rule comes in handy. Let's do this. Let me erase this whole thing and then we will get to it. So the first example that I'm going to talk about is carbon dioxide. Okay, so in this molecule, do you know the oxidation number of carbon? Not yet, because it is not covered in rules 1 through 8, so we don't know the oxidation number of carbon. So let's talk about the oxidation number of oxygen. Do we know the oxidation number of oxygen? Yeah, we know that according to rule number 7. Yeah, the oxidation number of oxygen is a -2. That we know. How about carbon? We don't know about carbon. Okay, I'm gonna use a pen because it is hard to write using this pencil. Okay, so let's sorry about that. So let's do this. So you have 2 oxygens, you have 1 carbon, and the sum of the oxidation numbers for this formula should be what? 0. You already know the oxidation number of oxygen, which is -2. You don't know the oxidation number of carbon. So 2 times 2, that is a -4. 0. So you take -4 to the other side. So carbon oxidation number is equal to +4. Okay, so the carbon oxidation number right here is +4. +4. Do we get it? Let's do another example. Let's erase this one. By the way, please feel free to pause and rewind and go through these rules again and again. Okay, let's talk about SO3 this time. Let's talk about SO3. Okay, so all right, do we know the oxidation number of oxygen? Of course we know the oxidation number of oxygen, which is -2. Do we know the oxidation number of sulfur? No, we didn't talk about it, so we don't know the oxidation number of sulfur. Okay, we don't know the oxidation number of sulfur, but we know the sum of oxidation numbers for SO2 is 0. So you have 1 sulfur and then 3 oxygen. If you add all these oxidation numbers, the sum should be a big fat 0, right? Okay, so you have 3 oxygens, so each oxygen is a -2, and then you don't know the oxidation number of sulfur. So 3 times 2 is -6. You take it to the other side, so it becomes +6. So sulfur oxidation number is +6. +6. All right, so let's do one more example. Let's do ammonia. So I'm going to use a different color now. Okay, so do we know the oxidation number of hydrogen? Don't scratch your head, you know. Okay, hydrogen is bound to a non-metal, so it should be +1. You know the oxidation number of hydrogen. Do you know the oxidation number of nitrogen? Let's say you don't know. Let's pretend that you don't know. Okay, so that is what we need. All right, so you have 3 hydrogens, so that hydrogen side is what? Hydrogen side is +1 times 3. This is +3. So what should be nitrogen? I mean, sum of oxidation numbers should be 0. So if hydrogen side is +3, nitrogen side should be what? -3. You guessed it correctly. You don't have to do all those equations to figure this one out, okay? Excuse me. Alright, let's do another example. Guys. Let's do PCl5. Alright, you know the oxidation number of chlorine because it is a halogen, you know that. So each chlorine is a -1. We need to figure out the oxidation number of phosphorus. This we don't know. I'll separate the two from a dashed line. Okay, do this in your head. Now 5 chlorines should be -5. So phosphorus should balance that. So phosphorus should be what? +5. You guessed it correct. Good job. So the oxidation number of phosphorus is +5. Well done. So let's do this. Let's do a more complicated one or something a little bit more challenging. Let's do HCO3. Let me use a different color. Let's use HCO3. All right. So you already know the oxidation number of, let's say, oxygen. How much is oxygen? -2. I mean, you have 3 oxygens, so you know the 3 oxygens are going to be -6. And then do you know the oxidation number of carbon? No, you don't. You don't know that. So you don't know that. Hydrogen, it is attached to a non-metal, so it should be what? It should be +1. Okay. So this right here is +1. Remember, we have to make them all equal to 0, right? So you have a -6 +1. So sorry, actually this formula has 2 hydrogens. I'm sorry about that. I don't want to do something that is technically incorrect. So this is, each hydrogen is a +1. So the 2 hydrogens are going to be +2. Okay, so +2 -6, to balance that, carbon should be how much? Carbon should be +4. Carbon should be what? +4. Well done. carbon should be +4, and this video is becoming really long. So, but I mean, I hope you get the idea now, right? Let's do another one. And I'm doing all these examples so that you will at